thanks a lot to the organizers for putting up this amazing conference, this great place. So yes, I'm going to talk about this recent work that we published together with Daniel Baumann, Gregory Mathis, and Guillermo Pimentel. So yeah, let me get started then with a bit of background. So as Enrico explained very nicely today, in the cosmological bootstrap community, we study correlators. Of operators that are located on the three-dimensional boundary of a four-dimensional bulk spacetime that is, we will consider that it's just a zeta spacetime. And due to the isometries of the four-dimensional bulk space, these boundary correlators are invariant under conformal transformations, and hence they are like CFT correlators, basically. Good. There is a huge challenge in our community, as Enrico explained today, which is that correlators of massless and spinning fields in cosmology are very complicated objects. And these massless and spinning fields in the bulk, these gauge fields in the bulk, they correspond to conserved currents in the boundary. So these correlators are effectively going to be just CFT correlators of conserved currents. And they are indeed very complicated objects. And well, I'm going to show literally the same example that Enrico was showing today that was computed by this graviton 4-point function at 3 level, written here in momentum space. It's what was computed in this paper by several people that are present here. So yeah, as you can see, it's very complicated. Cool. In contrast, we all know that scattering amplitudes in flat space can be written in a very simple way in terms of convenient variables. Which are these so-called spinor helicity variables, and there is the classic example of the Parquet-Taylor formula, which is this amplitude of n gluons in Young's theory, where exactly 2 of them have helicity minus, which can be written in terms of this beautiful formula that just fits in one line in terms of these spinor helicity variables. Well, if you want to write down the same amplitude in terms of momenta or polarization vectors, you would write down a super long and complicated expressions that may have like 100 or 1,000 terms depending on how many points, for example, at 6 or 7 points. And why is this amplitude so simple in terms of these variables? Well, one of the reasons is that spinor helicity variables trivialize all the kinematic constraints of our observable. Firstly, they trivialize the Lorentz symmetry of these amplitudes. And secondly, they trivialize, which comes from the space-time symmetries of like our Minkowski space. And secondly, they trivialize the fact that the particles that we are scattering are massless. And the way that they do this is by not being redundant variables. Like in these variables, there is no gauge redundancy whatsoever. Unlike other variables like moment and polarization vectors, for example, which are very redundant variables. Great. So taking this as an inspiration, maybe the reason why cosmological correlators of massless and spinning fields like gluons or gravitons are so complicated is because we are probably using inconvenient variables for them. So what variables are convenient? What are the right variables that we need to use? We'll take the approach that the right variables for them must make all kinematic constraints of these cosmological correlators manifest. So what are these constraints? Well, firstly, they have to be invariant under conformal transformations due to the isometries of the bulk spacetime. And secondly, they have to trivialize the fact that these particles in the bulk are massless, which corresponds to a conservation condition for the currents in the boundary, meaning that these currents have to satisfy this equation. They should be divergenceless. Hence, our goal in this project is to find new variables that expose the hidden simplicity of these correlators by trivializing all these kinematic constraints simultaneously, which is something that doesn't happen when we write down our correlators in the usual variables that we use of embedding space or position space or momentum space. In none of these variables we can trivialize these two constraints simultaneously. So we'll try to find new ones. And okay, and to find these new variables, we just follow our nose, okay? We just think, okay, first we need to trivialize conformal symmetry. People in the CFT community know very well how to do this. The way to do this is to go to the so-called embedding space, which is a higher dimensional Minkowski space where we can embed our boundary of our de Sitter spacetime. And the way to do this is by mapping three-dimensional positions to light rays in the null cone of a higher dimensional Minkowski space, specifically a 5-dimensional Minkowski space. So here we are indeed mapping like points, three-dimensional points to just light rays that belong to the null cone of this 5-dimensional Minkowski space, and hence I satisfy these 5-dimensional vectors satisfy p squared equal to 0, and they are projective. The beautiful thing of this map is that it translates conformal transformations in this three-dimensional boundary to Lorentz transformations in this 5-dimensional Minkowski space, in this embedding space. And hence, it is very easy to trivialize conformal symmetry in this language of embedding space. Because if we have like some correlator written in embedding space, if we just say that it only depends on products between embedding space vectors, then this is trivializing the first kinematic constraints that we had, which is conformal symmetry. However, this does not trivialize the conservation condition, because it's not trivial in these variables that these currents are conserved, that they satisfy that differential equation. Cool. Okay, so we just trivialize conformal symmetry, and now we need to also trivialize conservation. So let me tell you a nice lesson that we learned from studying 2D CFTs. Here the embedding space is 4-dimensional, and hence we can use the ordinary spinor helicity variables that we use for 4-dimensional to express a 4-dimensional massless momenta to express now our 4-dimensional position in embedding space, which belongs to the null cone of embedding space, right? And to do this, we basically express our 4-dimensional embedding space position as a 2x2 matrix, and then since this is a null vector, we can write this as the tensor product of these two spinors that we will call embedding space spinors. They are basically like spinor helicity variables. Okay, doing this procedure works well for all scaling dimensions, meaning for both conserved and non-conserved tensors. But there is something special that happens when we consider conserved tensors, which is that these tensors are actually holomorphic in the sense that they only depend on one of these spinors, on lambda, and not on the other, for example. They depend on lambda, not on lambda tilde. Hence, the lesson that we learn is that conservation is trivialized through holomorphicity, which makes sense because we already knew that in 2D CFTs, for example, the first energy tensor split into T and T bar, and holomorphic and anti-holomorphic P's, and same for the calculus of the current. But now the question is, how can we generalize this notion of holomorphicity that trivializes conservation to our case of interest, which is 3-dimensional CFTs? So let's turn to the case of 3-dimensional CFTs. And again, let's just follow our nose and try to play this at the same game. Well, here the embedding space is 5-dimensional, and hence we must now use the version of spinor helicity variables that has been developed in 5D flat space. And here there are some reference for this, and it basically consists on trading this 5-dimensional position in embedding space by a 4x4 matrix by contracting it with the gamma matrices of Minkowski 5. So we have this antisymmetric 4x4 matrix, and due to the fact that p squares to 0, we can express this 4x4 matrix as a tensor product of these spinors. So as you can see now, these new spinor variables are more complicated than before because they have like now two sets of indices. They firstly have like these capital A and B indices that are spinor indices that go from 1 to 4. And they also have this lowercase a and b index that is like a little group index. Because if you apply some transformation to this index, it basically doesn't change the embedding space position. That's why we call it little group index. Right. So in this, in terms of these embedding space spinors, we can express a current, a tensor, in terms of a tensor that has like 2s little group indices. Well, it depends on these spinors lambda. This is just like a change of variables. Yeah, exactly. And in terms of these lambda variables, and in terms of this current expressed as this tensor with little group indices, the conservation condition gets translated to some differential equation for this object, where here this operator is just some differential operator in terms of the lambdas. Essentially, at the end, it's just some derivative with respect to these lambda spinors. And we need to trivialize that condition now. So we need, again, some notion of holomorphicity appropriate for 3-dimensional CFTs that trivializes this conservation condition. Cool. And the way that we can trivialize this conservation condition is by considering holomorphic functions that only depend on these lambda spinors through one linear combination of them that we call set. So this spinor set is a linear combination of these two spinors that we call lambda 1 and lambda 2, and the coefficients of this linear combination are these pi coefficients. Right. And it turns out that we can interpret this object as a twister because we can see that this relation is a non-locant relation that maps a point in embedding space or in position space to a line in this space of spinors, and vice versa. We can map a point in twister space to a null line in the complexified 3-dimensional position space. Good. Yeah, so that's why we interpret it as a twister. Great. So okay, we just said that we trivialize conservation with holomorphicity. No? So we know that if we consider a function like this that depends on these two spinors only through that linear combination, then that will trivialize the conservation condition. However, a current in the left-hand side, like this one in the left-hand side, shouldn't depend on our arbitrary choice of these coefficients that we choose for this linear combination. Hence, what we can do is just to integrate over them, and just in order to just erase this arbitrary choice. And yeah, this is exactly what we are doing here. And also in this integral, we are adding like a bunch of factors of pi here in order to match the expected index structure in the left-hand side. And we get this formula. We can take it as like an answer for now. And it turns out that this a current that is given by this integral formula is automatically conserved essentially because at the level of the integrand, this object is holomorphic. The holomorphicity, the fact that this thing is holomorphic at the level of the integral ends up implying that when you hit this current with the conservation operator, it trivially vanishes. Essentially because at some point when you apply that derivative of the conservation operator, at some point there appears a factor like this that trivially vanishes because we're contracting something antisymmetric with something symmetric. Great. So, and moreover, since the embedding space position was projective and we didn't really care about its scale, then these lambda spinors are also projective and we don't care about their scale. And finally, we shouldn't care about the scale of these pi coefficients either. So this integral over the pi's must actually be like a projective integral, which implies that this integral should be invariant under rescaling these pi factors, these pi coefficients. And this implies that the integrand must scale with respect to its argument in exactly this way, in order to cancel out the scaling of the measure and all these factors. This implies that the scaling dimension of the current in the left-hand side, which tells you how it scales with respect to these lambda spinors, must be exactly given by this value, which is that delta is equal to the spin plus 1. Note that this is exactly the value for the scaling dimension that corresponds to a conserved current with spin S in a 3-dimensional CFT. So we indeed get precisely this value as expected, because if we wanted to trivialize conservation, then we better get the right value for the scaling dimension, and indeed we get it. Great. Okay, so this slide is a bit technical, but let me go through it. I just do a rewriting of the previous formula, essentially, which is to write it firstly in an index-free form by contracting the previous equation with some auxiliary vectors, these zetas, to absorb all the free indices, all these free little group indices. And then we get the first line here. And secondly, we can do like a change of variables from these pi coefficients to this twistor set, so that we just directly integrate over the twistor. And secondly, we also define this spin or upsilon in such a way that this factor of upsilon, this product of upsilon dot set coincides exactly with this contraction of this zeta dot pi. Note that these upsilon and zetas are basically polarization vectors or spinors that are essentially just absorbing all the free indices of our current. That's it. Great. So this is just a rewriting of the previous formula that we had, where the product here consists on contracting all these spinor indices with this symplectic form, this omega. Secondly, there is also like an alternative integral representation that trivializes conservation as well, given by an integral that looks like this, where note that now this upsilon is contracted with derivatives with respect to a spinor instead of with the spinor itself. And secondly, in this representation, we're integrating over a so-called dual twistor that we denote as W. And essentially it has like an index downstairs that is like a duality between the dual twistor and the twistor. But yeah, essentially it's just a twistor. Great. So, okay, the important thing to take away from this slide is that there are just two ways to trivialize conservation with these twistor integrals. Firstly, these integral over twistors, that is written here. Secondly, these are integral over dual twistors. That's it. But now, we just learned how to trivialize conservation for a single current. However, we are very interested in doing this for correlators. Very interested in trivializing this constraint for correlators that are located at multiple points. So let's just turn to the case of correlators and try to apply this idea to trivialize conservation for this. Well, let's consider the example of 3-point functions of spinous currents. And we want to trivialize that these free currents are conserved. For which, what we can do is to express this 3-point function as a triple integral over twistors, one per each external current of each of these free twistors. And yeah, similarly, we can do the same with an integral over 12 twistors with these other ansatz. And yes, and essentially, these two ways of writing down these 3-point functions trivialize conservation. And moreover, we can also trivialize conformal symmetry if we assume that the integrand of this representation depends on the twistors only through their product, where their product consists on contracting the indices with this omega. Great, so if we do this, then we're trivializing both constraints simultaneously, conformal symmetry and current conservation. And essentially, this allows us to interpret this integrand, both f or f tilde, as basically our correlator written in the language of twistor space, where both these constraints are manifest, while these integrals between square brackets are just a map that is translating our correlator in twistor space to embedding space or position space. Great, but as we can see, since all constraints are manifest and are trivialized in the language of twistors, then the right language to talk about these objects would be just at the level of the integrand of this representation. Great. So note also that since these free integrals have to be invariant in the rescalings, then these correlators in twistor space, f and f tilde, must scale in a specific way with respect to each of these free twistors. And we can use this scaling, this expected scaling, in order to bootstrap these correlators in twistor space, and indeed this is what we did. We just bootstrapped them via scaling, which was pretty simple, and then we arrived to like these formulas that here are written in this so-called Schwinger parameter representation or link parameter representation in terms of integrals over these parameters C12, C23, and C31 that we call Schwinger parameters. And essentially, this f and f tilde are just given by the integrand in this representation. Depends on these three parameters. And essentially, after imposing the right scaling, we find that these objects have this very simple expression. Either the product of the three parameters raised to the power of s, or 1 over that, which, as you can see, they are very simple expressions. Great. These correlators that we just bootstrapped in twistor space can be mapped to embedding space by computing explicitly the free integrals over twistors that were within square brackets before. Like, if we compute explicitly these free integrals, we can just map our twistor space object that we bootstrap to embedding space. And this is precisely what we did. We computed explicitly these free integrals and mapped the first twistor correlator that we bootstrapped in the first line to the free-point correlator in embedding space that arises from higher derivative interactions in the bulk, like f cubed for spin 1 or Riemann cubed for spin 2. And secondly, we also mapped the second twistor correlator to the correlator in embedding space that arises from leading interactions in the bulk, like Young-Mills for spin 1 or GR for spin 2. So again, let me remark again that these correlators in twistor space are very simple. They are way simpler than their counterparts in embedding space or in momentum space. Like, these objects look simple in twistor space, then the complicated part is just on computing the map to these other languages. And then indeed, in these other languages of embedding or momentum space, they look complicated. But the twistor space, at least at 3 points, they look rather simple. And moreover, another hint of this simplicity is that there is a very simple double copy structure at 3 points, because if you take this correlator in terms of the Schwinger parameters for Young-Mills, which is this for spin equal to 1, and you square it, you get this thing for spin equal to 2, which is the correlator that can be mapped to the GR correlator. It's the one that corresponds to GR. So essentially, we see that in this language of twistors, we have a very simple squaring procedure where we just square something, the correlator in Young-Mills, and we get the one in GR at 3 points. Which is something that does not happen in the other variables that we usually work with in cosmology, like momentum space or embedding space. There, the squaring procedure is more involved. And finally, let me mention that these objects in twistor space can also be mapped to known correlators in momentum space via a map that is called a half Fourier transform that has been also used to translate scattering amplitudes from momentum to twistor space. I can explain more details about this if you ask me later. Great, and now let me conclude. So in this work, essentially we found variables, novel variables that make all the kinematic constraints of our cosmological correlators manifest. And then we try to write down a 3-point function in terms of these variables, and we found that they are pretty simple compared to the other variables that we usually use, like embedding or momentum space. This is why we say that we expose a hidden simplicity of 3-point correlators by writing them in twistor space. And well, the next steps is firstly to extend this formalism to higher points and try to write down 4-point functions in this language of twistor space, and hopefully to deduce some way of connecting higher point correlators in twistor space to lower point correlators in twistor space that may allow us to deduce recursion relations, which might then allow us to deduce some cosmological Parquet-Taylor formula that would give us an n-point gluon correlator for all n Young-Mills theory, which would be great. We expect that if these are indeed the right variables, which given that they realize all the constraints, we hope that these variables are indeed the right language to work with cosmological correlators. Hopefully we can extend this to higher points. Great. And finally, since again these variables are like the best description of the kinematic data that we currently have, then they might be useful also to study geometries in the space of kinematic data, which can be connected to the observable that we care about, which are these correlators, maybe in a similar way as what happens in flat space, that where people interpret amplitudes as the volume of some positive geometry that lives in the space of kinematic data, for which usually people, the first thing that they do is just to go use variables, use the most convenient variables possible. People usually go to these momentum twisters to build the amplitude. So yeah, maybe these variables are useful for a similar interpretation. So yeah, that's it. Thank you very much.
Questions?
Okay.
Can I quickly clarify? So this was limited to 3 dimensions?
Yes, to a three-dimensional boundary, which corresponds to a four-dimensional bulk.
And does the DBI action simplify in these variables?
The DBI action.
Yeah.
So we directly focus on the correlators. We just try to bootstrap directly the correlators without choosing any specific action. But yeah, that would be.
The graviton 3-point function satisfies the soft theorem in the squeeze limit. Can you see that constraint from this twistor space structure? How does that come about?
Okay. So yeah, that's something that we didn't look at, like how the soft limit, which is taking like some momenta to 0, corresponds to in the language of twistors. That's something, yeah, that we haven't looked at, but yeah, would be interesting.
First of all, thank you for the great talk. So the integral you use to get the current so it kind of looks like what a Penrose transform, and normally Penrose transforms generate linear fields. So let's note, is there sort of, since this integral you generate the current looks like a Penrose transform, is there this restriction on the field that has to be linear, or could it be non-linear?
Is there what, sorry?
The current, so the integral you use to generate the current, normally that looks like a Penrose transform.
Yes.
And that normally gives you linear fields. So I just want to know, is the current in this case linear, or is it non-linear in some way?
I think it's linear. Yeah.
So if we start in an embedding space and apply conformal and conservation, usually you have like different pieces that need to combine to give you F cube or R cube, whereas here you just directly give F cube and R cube. So it sounds like you have already a notion of bulk locality, that these terms that you generate are one-to-one matched to bulk local operators. Because naively, if you just apply conformal and conservation and embedding space, usually you only have different terms that need to combine correctly, but here you just directly give it. So I guess I'm asking, is there a bulk picture of this that these forms are derived by a bulk, where the fact that you're just directly giving a bulk local operator is manifest?
At the end, in practice, we really don't use anything about bulk. We just work we just impose those two constraints and get at the end get these twistors that are related in some way with the boundary positions, which is that a twister would be like some null line in the complexified three-dimensional boundary. But then at the same time, this twistor also corresponds to something in the bulk, which is an alpha plane in the complexified bulk. So at the end, there is a relation with the bulk, but in practice, we don't really use it. And yeah, it would be interesting to see how to connect these variables with the bulk more explicitly. But yes, at the end, there is a connection. So.
Okay, last question.
Thanks for the next talk. We know that for Ward Takahashi identity, because you say you trivialize, you choose the twistor variable to trivialize the current conservation and special conformal transformation. We know that for correlator, it's conserved or it holds up to these boundary local terms. And I'm wondering, where are those terms? If you, like you choose a special gauge, or is it like you working in this integral round? Is they just go away, or?
So that's actually a pretty subtle point. And in order to practically do calculations, to practically be able to translate the Twister correlators to embedding space or momentum space, we have to do a weak rotation to a different signature where the boundary is Lorentzian rather than Euclidean. Okay? And then at the end, we analytically continue our result from a Lorentzian 3D boundary to an Euclidean 3D boundary. And in that step of analytic continuation, we go from a correlator that when we do the calculation, we also assume that all positions are space-like, and hence there are no contact terms. And then in that analytic continuation, we go to our correlator in Euclidean signature, and the result that we get after applying this analytic continuation satisfies the Wartag hash identity with the contact terms. So they arise from the analytic continuation. But in the signature in which we perform all the calculations, we don't see it. It appears after the analytic continuation. So that's actually a very subtle and interesting point that is worth to explore.
Okay, let's thank Facundo again.